So the voltage regulation of a transformer is defined as, let's write this down. The change in magnitude of the secondary terminal voltage from no load to full load conditions when the primary voltage is held constant. Okay. So mathematically, this is going to be expressed as a percentage. So we will say that the percent VR, so the percent voltage regulation, is going to be the magnitude of our secondary terminal voltage under no load conditions minus the magnitude of our secondary voltage, terminal voltage under full load conditions, all over the magnitude of our secondary terminal voltages under full load conditions times 100%. Typically speaking, this is going to be a few percent, okay? And I'm just going to make a note here where full load conditions mean that the secondary is supplying rated power, okay? So if I were to draw a circuit here, transformer equivalent circuit. So on the left-hand side here, I'm going to have my supply voltage. I'm just going to call this VS for what it's worth. And then I'm going to have everything referred to the secondary side of the transformer. So that means that I would have a voltage of A V1 here. Let me make this longer. This will be RC. Let's call it RCS because it's referred to the secondary. JXMS, once again, because it's referred to the secondary. Here's REQS, JXEQS. And here's V2, and then I'm going to put a generic load over here. And the purpose of this load is to just draw rated power, right? So what we could find by applying Kirchhoff's voltage law around this loop is that A V1 is going to be equal to V2 plus I2 times REQS plus J XEQS, and the magnitude of A V1 is literally the same thing as the magnitude of V2 under no load conditions. Okay. So let's work an example here then.
I have a practical question, but like, does this mean that every station coming from transmission essentially has step down transformer of some kind?
It definitely has to, yes.
Whether or not like specifically a step up or step down, or just like,
so on a distribution network, very specifically, so this is only tangentially related to what we're talking about today, but it's very related to the class, right? So all of the power and distribution transformers that are in service can be either a step up or a step down transformer, depending on how you're connecting things, okay? Now, there's nothing stopping you from connecting a lower voltage on one side, lower voltage on the side with less turns, and then getting a higher voltage on the side with more turns or whatever, right? Now, specifically, the service that's coming into our home is from the secondary side of what we consider to be a step down transformer, because when we transmit power over longer distances or whatever, we always want to do it at a high voltage because we have lower I squared R or ohmic losses. So here in Ruston, if I am not mistaken, the voltage that we would see in the transmission lines throughout the city are at, I believe, 13.5 kilovolts RMS. And then that is getting stepped down to 240 volts RMS for any single phase consumers like homes and things like that. And it's getting stepped down to 208 phase to phase or 120 phase to neutral for apartment complexes and things like that that utilize a three-phase system. So any kind of residence or anything like that is definitely going to be connected to the secondary side of a step-down transformer. But chances are, even in a commercial or industrial setting, you're also going to be connected to the secondary side of a step-down transformer, because it's not a whole lot of processes that require access to tens to hundreds of kilovolts RMS. Did that answer your question?
I think,
Okay. So this concept of voltage regulation is effectively about how good of a job the secondary does at maintaining its terminal voltage or its nominal voltage under various loading conditions. Okay, that's really all this is. So for a distribution transformer or something like that, we would want that voltage regulation to be rather small, because we don't want that voltage to change a whole lot when a bunch of people, let's say, turn on their ovens at the same time because they need to cook dinner, right? Roughly everybody's going to get off work. I say everybody. Most people get off work about 5, maybe they start cooking dinner around 6. So we should expect to see a relatively large power draw at that time. And we wouldn't want those, the secondary voltage to fall because of that increased load, that would literally cause blackouts and things like that. So we're going to talk about the voltage regulation. It tells us how good of a job a transformer does at maintaining that secondary voltage under specific conditions.
For CTs stuff coming up, right?
So CTs are, current transformers are used to measure, so CTs and VTs are used to measure the signals so that they know when to turn on relays and things like that, throw industrial breakers, or potentially when to engage things like static VAR compensators and stuff like that to make sure that there's enough VARs injected into the system to help it ride through. Yeah.
There's a thing I'm thinking of, I can't remember the name, but I know that we worked on one in the summer, and it was to help, it was to change, it allowed the transformer to like change steps in order to regulate that
Mhm.
voltage. I just
Yeah.
can't remember what it was called.
All right, so let's say that we have a 100 kVA. 7,200 to 240 volts RMS, 60 hertz transformer is tested, and the data collected is given below. So once again, these are going to be the results of the open circuit test and the short circuit test. And in this particular example, both the open circuit test and short circuit test were carried out on the high voltage windings. So let's say that the top thing is going to be the readings from the voltmeter. Then in the middle, we'll have the ammeter. And lastly, we'll have the watt meter. So let's say that our open circuit test gave us a VOC of 7,200 volts RMS, an open circuit current of 0.65 amps RMS, and a power of 425 watts. And again, all of those are measured on with the test being performed on the high voltage side. Our short circuit test gives us a short circuit voltage VSC of 250 volts RMS, short circuit current of 13.889 amps RMS, and lastly, a short circuit power of 1,420 watts. Okay. So the transformer is connected to a full load, meaning that it's drawing rated current and all that kind of good stuff, which operates at 0.90 lagging power factor. And we want to determine the voltage regulation of this transformer. Okay. So let's start by explicitly saying here, let's consider the primary to be the high voltage side and the secondary to be the low voltage side. So from this, our turns ratio is going to be, I have it as 7,200 over 240, but that's actually backwards. So this must be from when I made notes in a previous time. So let's work it the way that we would be doing it, right? So we define the turns ratio as N2 over N1 thus far in this class, right? I'm misremembering that. Okay. So in this particular case then, if we have our primary, so that's going to be the ratio of the low voltage to the high voltage. So that's going to be 240 over 7,200. Let me a calculator here real quick. One over 30. So that's what our turns ratio is going to be for this particular guy. Okay, so now let's go through and we're going to have to figure out all of the equivalent circuit parameters for our cantilever model. And this is going to be with everything on the high voltage side, right? So we would have our core resistance on the high voltage side is going to be the ratio of the open circuit voltage squared divided by our open circuit current. So that's going to look like 7,200 volts RMS quantity squared over 425 watts comes out to be 121.976 kiloohms. Our magnetizing reactance XM on the high voltage side is 1 over the square root of the open circuit current magnitude over the open circuit voltage magnitude, quantity squared, minus 1 over RC quantity squared. All of this is underneath that square root sign. I'm not going to write out the numbers here, but this comes out to be 11.122 kiloohms. Our equivalent resistance on the high voltage side, so this is from our short circuit test, is going to come out to be our short circuit power divided by our short circuit current magnitude squared. So this is going to look like 7.361 ohms. And our XEQ on the high voltage side is going to be the square root of the magnitude of our, short circuit voltage over short circuit current squared minus REQ HV. And from this, we get 16.426 ohms. So let's look back at our equation here, okay? So ultimately, what we need to figure out is 16.426 ohms. So our ultimate goal in this problem is to figure out the voltage regulation, okay? So what is V2 under full load conditions? Let's start there. So what is that V2 full load thing? Exactly right. It is literally just the rated voltage of the secondary, right? So this guy right here is literally just 240 volts RMS. And since that's just that same thing repeated, we have that 240 volts RMS there. So really the only thing that we need to figure out in order to do voltage regulation is this quantity V2 no load. And I literally have an expression for it right here, right? So in order for us to figure out V2 no load, we need to know what V2 is under the conditions, I2, REQS, and XEQS, right? So REQS is the equivalent resistance on the secondary side. XEQS is the equivalent resistance, excuse me, the equivalent reactance on the secondary side. So realistically, we need to convert these over to the secondary side, okay? We don't really need to worry about the RC and the XM because they're not showing up in any of the relations that we're interested in, right? So to relate this from the primary side to the secondary side, or from the high voltage side to the low voltage side, what do we need to do in this case? Are we multiplying by A squared or are we dividing by A squared? Multiplying by A squared, right? So REQ low voltage is just going to be REQ high voltage times 1/30 quantity squared. So that's going to look like 7.361 divided by 900 effectively. And this comes out to be 8.179 milliohms. Similarly, XEQ low voltage is going to look like XEQ high voltage, also multiplied by that factor of 1/30 squared, which is going to come out to be 18.251 milliohms. So how are we going to find, and the reason why I'm asking this specifically, let me go back up to this equation, right? So we just figured out what this guy is and what this guy is. So how might we figure out what I2 is? So we know that our load is effectively a full load. So we are delivering rated power, right? So that means that the S, let me call this SL for right now, is going to be simply the product of V2 times I2 magnitudes. So my apparent power, in other words, is just the magnitude of my voltage times the magnitude of my current, and that's the power at the secondary, which is why I have those subscripts V2 and I2. Do we all remember apparent power being just magnitude of voltage times magnitude of current? So I could rearrange this and say that my current I2 is going to be my apparent power divided by the magnitude of my load voltage right there. And so that's just going to be 100 kilovolt amperes over 240 volts RMS. And this comes out to be 416.667 amps RMS. Now, if we look back at our equation, we don't need the magnitude of I2. We need all of I2. We want the RMS phasor. So we have part of that. Now we need to sort out how to get our phase angle, okay? Well, our phase angle, if we assume and this is a fairly okay assumption because it's not really going to make that much of a difference in the end. If we assume that the angle of our voltage at the secondary is 0, then we can use our power factor to figure out what the angle of our current is with respect to that assumption of 0. Because realistically, if we assume V2 is 0 or has a phase angle of 0, I2's phase angle is going to be whatever it is. If we assume the phase angle of our secondary voltage was 43 degrees, I2 would still be the same amount away from that reference assumption. So in the grand scheme of things, it's not going to hurt anything for us to make an assumption here. I'm going to assume 0 because it just makes the math easier. Okay. So the angle of I2 is going to be negative the inverse cosine of the power factor. Now, you may be asking yourself, why the hell why do I have that negative sign right there, right? So let me explain that just really quickly, okay? So we know that in general, complex power is V times I conjugate, right? So because I'm having the conjugate in my expression right here, that means that I flip the angle on my current. So I'm going to include that negative sign out in front of my inverse cosine to correct that conjugation. Okay. So realistically, if we had another way to think about this is if we're assuming that theta V is 0, theta I would need to be negative for theta V minus theta I to come out to a positive quantity because we know that our power factor is lagging. Okay, so two different sides of the same coin, but regardless, that negative sign there is necessary to make this work out correctly. So we're going to do the inverse cosine of 0.9, negative of that, and so that's going to come out to be negative 25.842 degrees. And putting these two pieces of information together, we are going to have I2 is equal to 416.667 with an angle of negative 25.842 degrees amps RMS. And so from here, we can say that AV1, whatever that happens to be, and that's what we're trying to find actually, is V2 plus I2 REQ S, or low voltage, plus J XEQ. I'm going to put LV there so that we're consistent. Sorry. And so explicitly writing this out, we're going to have 240 angle 0 degrees volts RMS plus 416.667 angle negative 25.842 degrees amps RMS times 8.179 plus J 18.251 milliohms. And this comes out to be 246.440 with an angle of positive 1.245 degrees volts RMS. And thus our percent voltage regulation is going to be 246.440 volts RMS minus 240 volts RMS all over 240 volts RMS times 100% gives me 2.683% voltage regulation. So this particular transformer does a pretty good job. The secondary voltage really only changed by 2.683% under those conditions. So let's work one last thing here really quickly. I'm mainly adding this because once we get into our machinery, we're going to be talking about efficiency a whole heck of a lot, okay? And because so many of the things that we're going to be talking about when we're talking about our rotating machinery are going to be related back to these transformer equivalent circuit models, for what it's worth, an AC induction motor is literally just a transformer where we allow the secondary to rotate. This will kind of help lead us into that. So in general, the efficiency of a transformer as defined as eta, so that's a Greek N looking thing, is equal to the output power, and that is the average power, divided by the average input power, okay? Eta. It's a Greek, looks like an N, but technically is an eta. Yep, same, should be the same across the board, yeah.
Yeah.
Write it as a damn N, man. As long as you know it's efficiency, it's efficiency. So we can express the input power in another way as, so let me put P out up here again. So the input power is nothing more than the output power plus any losses that we have, right? That's the difference between those two quantities. So I could write P out as, excuse me, P in as P out plus P losses. And in this case, I'm going to take into account specific losses for our transformer. So we are going to have our core losses, and then we are going to have what are called our copper losses. Okay. So our core losses are literally what we measured as POC in our open circuit test, right? Because we don't have any current flowing through our secondary winding or anything like that. So we don't have any current flowing through the REQ, the series portion there, because that side is open circuited. Any power that we see is what is being absorbed in the core. So those are our core losses. And then similarly, our copper losses are the losses that we see in the windings of our transformer, which happens to be literally what we were measuring with our watt meter in the short circuit test. So this is PSC. So from these two pieces of information, we should actually be able to figure out what our efficiency is for the transformer from our previous problem, right? So I want to expand this out a little bit more, okay? OC is open circuit, SC is short circuit. So just to be real clear here, POC is something we measure during the open circuit test. PSC is something that we measured during the short circuit test. So if we wanted to calculate the efficiency from our previous example, the only thing that we don't know right now explicitly is our output power, but I think we can probably figure it out pretty easily, okay? So anybody have any thoughts on how we might figure out our output power? So just as a reminder, I know I gave you guys like 2 seconds to remember this, but let's be honest, you don't remember a whole lot from 280. Neither do I, for that matter. But let's go back to the definition of power factor really quickly, right? So power factor, we defined it as the cosine of the power factor angle. We used that guy a couple of minutes ago to effectively figure out what our power factor angle was. But a more fundamental definition for power factor is that it is the ratio of average power to apparent power, right? So I would argue that we could find average power by simply multiplying apparent power by the cosine of our power factor angle. So this is literally just apparent power multiplied by power factor. So if I wanted my output power, I would take the apparent power at my output. For the problem that we just had, where we had a fully rated load, what is our output power? What is our power? I heard 240, that's the voltage. Voltage and power ain't the same thing.
That's our, well, that's our 240 times our I 2 times something else.
Look at the board real quick, Zach. It's the 100 kVA. That is our rated apparent power. So if we have a rated, if we have our secondary of our transformer is delivering full load, it means it's delivering 100 kVA by definition. So we could do math if we wanted to, but I'm real lazy, so I'm not going to. So we would have 100 kVA. What was our power factor again? 0.9, right? So that's going to effectively give us our power in watts. And then 100 kVA times 0.9. What was our POC? 425, I believe. What was our PSC? All right. And so let's literally just throw this in our calculator. Just to be clear here, 100 kVA, so that guy is 1,000 times larger than the 425 is measured in watts. The 1420 is measured in watts. So just be careful with the units there, okay? So if I throw this into my calculator, I would have 100 times 10 to the 3 times 0.9 over 100 times 10 to the 3 times 0.9 plus 425 plus 1420 comes out to be 0.97991 and some change, or 97.991% efficient. So for what it's worth, power and distribution transformers, which is what we've mainly been talking about here, typically operate at efficiencies above 95%. So this is actually a pretty reasonable thing here. All right, so that is the last of our material for exam 1, voltage regulation, and that little chunk about efficiency, which is, I hope, voltage regulation can be a bit odd to wrap your head around. Efficiency hopefully shouldn't be. So before we move on from there onto our next big topic, does anybody have any specific questions? All right. So I'm going to start this next stuff on a whole new page. This is only the second time I've literally ever taught this material. So if you have any questions about it, please feel free to ask and I will try to clarify things, okay? So what we're going to be talking about now is the bridge effectively between transformers and motors and all of that kind of good stuff. And so this is going to be called electromechanical energy conversion. So, according to the law of conservation of energy, energy is neither created or destroyed. It is simply changed in form, okay? So the role of an electromechanical machine, like a motor or a generator, is to transmit energy across a system by converting it from one type of energy to another. So let's consider a simple motor system. So on the left-hand side, I'm going to have my source, okay? So I have an electrical system like so. And the output of my electrical system is going to be some sort of power, right? So just for the sake of argument, I'm going to draw a current I leaving this guy, a voltage V across the terminals. And I'm just going to make a little note here that P is equal to I times V. So this is my input power to my system, okay? Now in the middle, I'm going to have my motor, and I am going to draw that as simply a circle with a big M standing for motor. And then what I am attempting to draw here, this line is just going to be representative of the shaft of my motor. So I'm going to just make a quick assumption here. My shaft is turning in this direction. So it's going to be spinning at some angular velocity omega, and it is going to be producing some amount of torque, capital T, so that the output power of my motor, P, is going to be simply my torque times omega. So I've got an electrical input. Let me just make a note over here. And then I've got a mechanical output. And then my shaft will be connected to some mechanical system that I'm going to consider my load over here on the right. So in this particular simplified example, the motor is an electromechanical energy converter, right? It takes electrical signals as its input, or electrical power as its input, and it produces mechanical power at its output. If we had instead, let's say, a generator, it would be this exact same picture, but the direction of power flow would just be opposite. We would be putting mechanical energy in. Our generator would be converting that mechanical energy into electrical energy, and then our load would be the electrical system. But that's really, motor and a generator are the same thing. It just depends on, are we connecting it to mechanical power or are we connecting it to electrical power? Okay, so they're literally the same thing. And when we get to synchronous machines, we will literally do that, okay? So this is a very, very simplified version of what's going on, okay? In an ideal system, all of the input power and energy would be delivered to the output. But in a real system, this efficiency is never 100%. And so what I want us to do is look at the energy conversion process as a kind of general thing to understand what's going on. So for this system, our energy conversion process looks something like this. So over here on the input side, we have our electrical system. As an intermediate step, and this is really the key to electromechanical energy conversion, we're going to have what's called a coupling field. Okay. So this is either going to be an electrical field or a magnetic field. In 99% of applications, this is usually a magnetic field. Everything that we're going to be talking about in this class, it's a magnetic field. Okay, so electrical field as a coupling field is very, very rare outside of research laboratories. And then lastly, on our output side, we would have our mechanical system. Like so. And I'm going to put a little arrow like this, and this is just going to say P mechanical. So this is literally the output power that we're measuring from our system, and for what it's worth, I could put P electric over here if I wanted to for the electrical input power going into everything. Okay. So ideally, this is how it would work. But we need to take into account losses and things like that. Okay. So I'm going to draw these losses as arrows where we have energy or power leaving our system. So the first kind of losses that we are going to see would probably be electrical losses. So some of the electrical losses that we might see are literally the things that we've already described on our transformer, right? So we are going to have energy lost to effectively heating up our wires as they carry current. So those I squared R or ohmic losses, that is a form of electrical loss. We lose some amount of energy magnetizing the core of our system, right? Particularly when we have a magnetic field as our coupling field, right? We're going to have a core, typically a ferromagnetic core, so that we can hold a bunch of magnetic field energy in there, but we are going to lose some energy to magnetizing that core. So we've got electrical losses. Then we're going to have field losses, right? So we've already kind of talked about this a little bit. So this is like our flux leaking out and all of that kind of good stuff, okay? And then over here in our mechanical system, we might also undergo mechanical losses. So what are some of the mechanical losses that you think we might see in our electromechanical energy conversion systems? Friction, that is by far the biggest one, right? So friction, air resistance, all of that kind of good stuff. We're also going to have what's called windage losses. We'll talk about those a little bit later, but friction's the big one, okay? So nothing particularly wild or crazy there, okay? So we can essentially write an equation which is governing this behavior. where we would have, and this is for um, a motor system, we would have electrical input energy is going to be equal to the energy stored in the coupling field plus the mechanical output energy and then finally plus any energy losses that we may incur. So from this particular relationship, we can see that our output energy will always, always, always be less than the input energy. And the coupling field is effectively what is sustaining this energy conversion process. So without it happening, effectively taking in energy, storing it, and allowing it to be converted, we wouldn't have electromechanical energy conversion. So we can rewrite this equation a little bit by effectively distributing losses, okay? So if we wanted to, we could write this as, let me just put an arrow down here, like so. Electrical input energy minus copper losses, I squared R losses, will be equal to the energy stored in our coupling field plus our core losses plus our mechanical output energy plus our friction and windage losses. Over some small time interval dt, this equation can be written as dWe is equal to dWf plus dWm, where this is our differential electrical energy. This is our differential field energy. And lastly, this guy is our differential mechanical energy. So because we're probably least familiar with this aspect, I want to talk about our field energy first. Let me know when I'm good to move on to a new sheet of paper, as it were.
Coupling, electrical coupling.
All right, we good? I see people playing on their phones, so I'm going to assume I'm good. All right, so field energy. So I'm going to draw a picture of something real quick. So that should be enough room. So as I believe I have done previously, this red here is for a core, like ferromagnetic core material or something for part of a magnetic circuit. Okay. Where I'm going to call this bit right here LG for the length of my air gap. And as per usual, I'm going to wind up wrapping a wire around my core. Like so. And I'm going to say that my current I is flowing into the winding as I've drawn it, and that my winding has N turns. Okay. So I'm going to also add a little bit of an electrical input system over here on the left, which is simply just going to be some sort of source voltage. For now, excuse me, let's assume that this is a DC quantity connected in series to some resistance R. Let me just do it as R without the S for right now. And the voltage induced across my coil will be lowercase e. Okay. So let's say that this guy right here is the stationary part of my system. And I'm going to do something that we haven't really seen before. Let's say that this leg over here to the right is connected to a spring. And then the other side of the spring is anchored like so. And so I'm going to call this as my reference position. And this will be my X direction. So because that right leg is mounted on a spring, we're going to assume that this part over here is a movable part. So before we get into the nitty gritty of what's going on here, can anybody tell me what this thing is fundamentally? Exactly right. This is literally just a relay. We energize the coil, it causes the other side to collapse, and then there would be electrical contacts here and here that would connect to another circuit or something. But yeah, this is literally just how a relay works. Okay. So when I energize my coil, I should see flux traveling around my circuit like so. So I'm just going to make a quick note here. This is my magnetic flux. So if this system is at equilibrium, And so for equilibrium to happen, we would need the gap to be constant, right? So that means that the spring is no longer compressing or expanding, just whatever gap I have is fixed based on the particular amount of electrical energy I have in. We also would need the constraint that our current is also constant. So under these conditions, then our differential mechanical energy must be zero. There is no movement. We don't have any mechanical energy whatsoever. And thus, our differential electrical energy is the same thing as our differential field energy. So if we look at our diagram, our differential electrical energy, dWe. So just as a quick aside thing here, what is electrical energy? Go back to your literally, I think your ENGT 120 class maybe. What was electrical energy back then? So let's maybe start with something easier, okay? What's electrical power? I times V. Okay. What's the relationship between power and energy?
Power is the energy used.
So power is energy over time, which means energy is power multiplied by time. So if I wanted differential electrical energy and my voltage and my current are constant, I would have E, that's my energy across my coil, or my voltage across my coil, I, which is the current flowing through the coil, and then because we're dealing on things differentially over a very small time interval, my T is just going to be that small change in time dt, okay? And this is, once again, dWf. My induced voltage, E, is the change in the flux linkage with respect to time. Talked about that several class meetings ago. So from that, if we substitute in that relationship for E, we'll get dWe is equal to change in flux linkage with respect to time multiplied by current times change in time. Those guys, this dt and this dt here, just cancel each other out. And so I wind up getting I times the change in flux linkage is equal to my differential field energy, and therefore my field energy is just the integral from 0 to any particular value of flux linkage of I times integrated with respect to flux linkage. Okay.
We're actually gonna do the interval,
Um,
or are we just gonna kind of?
we're gonna talk about what they mean and then go from there without having to legitimately do the integration, which is literally the next thing that I'm going to be talking about here. Okay. So the relationship between coil flux linkage and current for a particular air gap Goodness, that looks like shit. Looks like this graph. Okay. So I'm going to put flux linkage on the y-axis and current on the x-axis. And it's going to look something akin to this. Where everything up here above this curve is what we're going to call the energy. And everything below the curve is what we're going to call, excuse me, the co-energy. Where co-energy is going to be WF prime. Okay. So for what it's worth, this little slice right here is our differential field energy, dWF. Okay. So we should be able to see that our co-energy, sorry, let me make that a better subscript. WF prime is greater than our field energy WF, and for what it's worth, I could define my co-energy as the integral from 0 to I of flux linkage with respect to current. So this characteristic curve depends on air gap length. I think I've mentioned that to you before. So that if we had multiple different air gap lengths, we would get slightly different curves. Okay. So yes, co-energy. So energy is the area above that curve, co-energy is the area below the curve. Okay. All right, so the flux linkage to current characteristic curve depends on air gap length as well as the BH characteristics of the core material. So if I were to draw a similar set of curves for a particular material with varying gap length, it might look something like this. So here's lambda. Here's I, and let's say that this curve right here corresponds to some gap length LG1. This curve right here corresponds to some gap length LG2. This curve right here corresponds to LG3. And I'm just going to make a note. These are increasing gap lengths, meaning that LG1 is shorter than LG2 is shorter than LG3. So that as we make that air gap larger and larger and larger, it tends to linearize the relationship between current and flux linkage. We actually talked about this before, about how the air gap tends to linearize the inductance of a coil. That is literally the exact same thing that's going on here, because we know that flux linkage and inductance are proportional to each other, okay? So for a system where LG is large enough to linearize the flux linkage current curve, our co-energy, WF prime, will be equal to our energy WF, and this will literally just be 1/2 times our flux linkage times our current. It's literally just the area of a right triangle. Right? So in a magnetic circuit, we know that our MMF is equal to N times I, and this is the closed line integral of H dotted into DL. And we could rearrange this to find that our current I is then the integral of H dot DL over our number of turns. We also know that our flux linkage, sorry, that gamma looks like shit, is equal to N times our magnetic flux, where our magnetic flux could be written as our area multiplied by our B field. And so using these relationships, we wind up getting our field energy is the integral from 0 to flux linkage of I times the derivative of flux linkage. And so I'm going to integrate the integral of H dot DL over N times N A dB. And then I'm going to just expand that line integral of H dot DL out into the H field in the core times the length of the core plus the H field in the air gap times the length of the air gap all over N multiplied by NA dB. Okay. For what it's worth, I don't know why I didn't do this sooner. These N's cancel each other out. And I can put my H field in terms of my B field by dividing by the permeability, right? Right now I have some things in terms of H and I'm integrating with respect to B field. So, excuse me. So instead I could write this as the B field in the core divided by the permeability of the core multiplied by the length of the core plus the B field in the air gap divided by the permeability of the air gap, which is the permeability of free space, which is why I wrote it as mu naught, times the length of the gap, all times area integrated with respect to B field. I promise I'm almost done with this crap. Will be equal to the integral of BC mu C times dB multiplied by A times LC plus the integral of BG over mu naught times, excuse me, integrated with respect to dB times a LG. And now I want us to kind of look at some things here really quickly. Okay. So this integral term right here is the energy density. In the core. So this will be WF subscript C, okay? And very similarly, this guy over here will be the energy density in the air gap. So we'll do this as dWFG. What is this cross-sectional area times the length going to be? So just to help you guys out. Exactly right. That is just volume. So that's just the volume of the core. Let's call it VC. And then over here, we would have air gap volume, which we'll call VG. Now, I'm integrating B with respect to B. So do you guys, how familiar are you guys with integral? What's that? There shouldn't be a D here. Thank you for that. It's no longer a differential thing after we integrate it. So thank you for that.
That's lambda. What happens to that?
The limits of my integration, I kind of just hand wave them away because we changed variables essentially. So realistically, it should be from 0 to whatever B field we happen to have in the part that we're looking at. But we're about to just dump this integration out into a specific equation per se, which is why I wasn't particularly worried about it. So generally speaking, what's the integral of x with respect to x? You guys done 1/2 x squared. So we literally have the same thing here. We're integrating b with respect to b. So this is all of this ugly, terrible math winds up just coming out to be BC squared divided by twice the permeability of the core multiplied by the volume of the core plus BG squared over twice mu naught times the volume of the air gap.